The next topic we need to cover in the Foundation series is line coding. I'm not going to spend a ton of time on this, but I think it's critical to have an understanding before moving forward. Please understand, I'm boiling down a complex topic. Some of the details are being excluded, as I'm not sure it makes sense to dive deep into the weeds if you aren't doing this as a career. I just want to tell you up front that I'm simplifying intentionally. The basic goal of line encoding, or line code for short, is to prepare the bit stream for transmission over a physical media. This work all happens within the network interface on any modern system, and is designed to be done quickly enough that it should never be a speed limiting factor. Line code development seems to always follow a pattern. The first versions for a given media type, fiber, twisted pair, coax, etc., is to use an on-off structure. This structure is simple to implement as on is 1 and off is 0. Remember, at the line code level, we're dealing with a bit stream, so there are only binary values being sent. The classic example of this is the telegraph. When the technology was first invented, there was a lot of work to figure out an efficient way to use the two possible states to communicate. Very quickly, they found they could make use of the duration of state to form the classic dashes and dots. This is a perfect analogy for how any new transmission technology is introduced. In the case of the telegraph, the largest issue that comes up is naturally resolved by the power of the human mind at both ends of the signal. That's timing. How to know when one letter ends and the next begins. Let me explain. If you transmit a string of ones, then the light is blinking, so both sides can keep track of how many ones have arrived, and any minor timing slips between them don't matter. However, if you are transmitting a string of 100 zeros, which isn't common at all, mind you, and you have a delta between the clocks on both sides of plus or minus 1%, then when the first one is received, the result could have been 99, 100, or 101 zeros, followed by a 1, depending on the timing error of the two clocks. Needless to say, ambiguity in networking always results in an error, as it should. The next step is to move towards a nominal value. That is a voltage or light intensity that's used to represent 0. This means that rather than having to start or stop the power or light, you can just change it to denote the transmission. It's a little like a light switch. The first step is on-off. The second is setting a value and then dimming or brightening the light. You can get a much faster response by using a dimmer. This is just an example. There are a few methods to accomplish the modulation, but we're going to go with this one. Given those factors, let's look at two of the early line codes that show the evolution over time. As you can see with AMI, you have two values. At the top, we have the data. That is the bit stream of ones and zeros. Below that, we have the line code. In this case, we aren't turning the power on and off. The power has a baseline value represented by the blue line. The signal is then modified in some way to create a change that will represent a fixed state for a 1. The next 1 will result in that same change, but in the opposite direction. This was done because if you try to use the same polarity or direction of change, then the baseline can slowly creep upwards depending on many factors, and eventually it may raise to the point that the detection equipment can no longer tell the difference between a 1 and a 0. To keep the timing in AMI, every 8th bit is just set to 1. This results in a capacity loss from the theoretical 64 bits a second to 56 bits a second, as 1/8 of the capacity is used for a fixed value, which is only to cover the case when more than 7 zeros are transmitted in a row. Now let's look at B8ZS. This is a much more interesting solution, as it used an error state to convey information. Not ideal, but very cool. What B8ZS did was inject a polarity error into the line. That's when the voltage is moved in the same direction 2 times in a row. This was actually a pre-formatted 8-bit string that the other side knew was representing 8 zeros. Because it contained a violation of the normal line coding rules, it would never be triggered by the bit stream accidentally, and thus allowed for the full use of all 8 bits for data. By pre-formatting this structure, it was possible to include opposing bits to keep the baseline from migrating. That's why you see a +1 before the 2 -1s in a row that are the polarity error, followed by another +1. For Ethernet, the method used to solve the timing problem was very different. Rather than modify or constrain the bit stream to inject timing protection, the bit stream was processed prior to transmission such that each 4 bits of data were mapped to a predefined 5-bit string. By doing this, it was possible to ensure that no data stream would result in enough of the same value to impact timing. This did, however, mean that the data on the wire was 20% overhead. To give you an example of how odd things were getting, for fast Ethernet or 100 base TX, there were 3 layers of encoding. First was 4B5B. That did the mapping I mentioned before. Next, it was encoded with NRZI, or non-return to zero inverted. And the final encoding done for transmission was MLT3. Now, we don't need to go into the details of all of that, but it does drive home just how much work is done at the network interface to prepare information for transmission. In this early example, there weren't encoding options available that would solve all the problems, so the line code was stacked to accomplish all that needed to be done. Finally, we get to the modern world with gigabit Ethernet. This is where things get complex. In fact, there isn't an easy way to represent it. So cut me a little slack here. The first thing to know is that Gig-E requires all 4 pairs, while 100 base TX only requires 2 pairs. Secondly, the 8 bits are sent across the 4 transmit wires at the same time. To accomplish this, 2 encoding structures were used. The first is TCM, and the second is PAM5. I'm not going to get into as much detail here, but the result is that the encoding requires 2 values on each side of the baseline. Each of those 4 steps represents 2 bits. So a +1 would represent 1, 0, and a -1 would represent 0, 1. And that, with making use of all pairs of wire, along with some other electrical engineering wizardry, and you get a total of a 10 times speed increase. Again, this is a very simplified description. Technically, there are 3 bits per step, and the process is much more complex, but I think this description will get the basic point across. We're undergoing a similar shift in the optical world with something called coherent optics. Right now, optics are using PAM encoding and function much in the same way as Gig-E does, only with an optical medium. However, coherent optics use a laser that produces a fixed beam at a specific wavelength. That light is then split and sent into 2 modulators that use some amazing techniques to encode the bit stream onto them. Then they are recombined into a phase-shifted version of the same wavelength. This not only allows for more data, but if the waves are combined properly in just the right phase, they can actually support one another and increase the transmission distance. Honestly, this is one part I sort of get intellectually, but I have to just trust the experts, as I couldn't explain why that's the case without confusing everyone involved, including myself. The use of a static light source with two phases and the ability to manipulate each in flight is how we are getting optics that can push up to 400 gigabits per second on a single wave. And with the math worked out, we can get up to 1.6 terabits per second as soon as the ASIC engineering and manufacturing is ready. Okay, I'm sure I've melted enough brains for one video, and going any further wouldn't add much value. I hope you can take away from this the high-level concept of how we encode data for transmission and what it looks like on the wire. Next, I'll be covering addressing, and then we can dive into Ethernet in a home network. The idea is to go step by step across the path the data takes from a gaming PC on a home network to the data center. In following that path, we will hit most of the fundamental technologies used in the modern internet. If you found value in this, please like. To keep up to date on new topics as they are released, hit that subscribe button. Thank you very much.